Or just,
no, that's fine. Oh, yeah, anyway, done the introductions. I just thought I'd put this in just to interest knowledge. AMRC. So we're in design, that blue building at the front. Going from left to right, we've got the training centre, which is lots of apprentices, and they do lots of mechanical things of filing and drilling and turning and things. I'm not entirely sure how much sort of software and development kind of things that they actually do as part of their MBQs or qualifications, and obviously the nature of Sheffield and things, and it's not renowned for software related career paths. But anyway, and then you've got design where we are. So outside you've got mechanical, mainly mechanical design engineers. We've got a couple of guys who look at VR and those type of AR applications as well for the manufacturing bias, really. So that's where we are. Just through there's the kitchen toilets are the medical AMRC, so they are sort of tasked with medical applications, really. They do have more medical bias projects coming on side that require electronics and control, etc. Structural testing, lots of big bits of metal, and they stretch them and test them, really. So there you go. That's what they do. Just down there. Factory in the future. If anyone is relatively interested, I'm happy just to towards the end have a little wander around. Essentially, lots and lots of very big metal making machines, and making metal smaller in many different ways, however you choose to do it. So, Factory of the Future was really born out of the ability to machine titanium quicker and cheaper than anyone else. So, if anyone's interested, happy to do that. Nuclear is very impressive building all the way up there. Again, huge machinery. There's machines up there that can take up to 60-ton work pieces of things. It's impressive in terms of the scale and things, but that's big engineering, big industrial capital expenditure and things, so we'll do that. CTI, which is castings, don't know too much about other than they cast. IMG is the integrated manufacturing group, so they do robotic cells, and they're looking at all of that side of manufacturing processes. They're actually moving over onto the airport site with the 2050 building, so they're actually moving through. And then the KTC, which is Knowledge Transfer Centre, which is all sort of PhD and research people that are doing projects for partners or whatever. So that's a very quick overview snapshot and things really. Questions or things?
So these all have some affiliation to
Yes.
Sheffield Uni?
Yes, so essentially I've described the AMRC is a high value manufacturing catapult centre, one of 7. I believe there's one at Coventry, there's one up at Edinburgh. Yeah, and there's a printed electronics up in Sheffield, I can't remember anyway. And we are a faculty, potentially, you could say, of Sheffield University. That's kind of how it works. It's all a bit grey, and that's the whole point, really. Here we've got manufacturing influence, Rolls-Royce, and all these different companies, but then you've got the academic side of research and that side, so it's all geared towards trying to get things up the TRL stage.
So just out of interest, the people who work for University of Sheffield?
Yes, yes.
Okay.
No, University of Sheffield employees. It's just the tagline of going because they were the
Put some money.
Yeah, they were the first people to put some money in to grow Factory of the Future out of was testing.
Okay, cool.
So yeah, so that's that. So there's two things I was going to discuss today. Really, we've got one project that is looking at machine process monitoring. And take a few minutes, and that was the outline of what the project was hoping to achieve. That those sort of points are: there's a process monitoring group that want to better understand their machining capability. So when you have a big fixture like a part for an aeroplane or something, how you machine that is quite important with respect to cutting parameters, feed rates, all of these other things that go into how you make that part, and ultimately the cost associated. So sometimes you may have very, very expensive cutting pieces, and the cost of the machine is quite expensive. So if you can reduce the time taken to machine that piece of metal, then you're increasing efficiencies and other things. So this is where the driver is for this particular project, and those are some of the things. So I shall do the other one, which is not a machine monitoring process. It's the laser sintering one, and I'll show you a video once I've gone through that. So those are the only real two sides. The other thing is the framework diagram behind you over there. So, and then I'm going to try and do a bit of a demo of all of it hanging together. So we'll see. So on the left-hand side, you've got what we're looking at is a target process, and that could be anything really. If we took power monitoring of the spindle motor as one of our target processes, that is the thing of interest that you want to monitor and better understand. And one of the points there being scalable and flexible. And the aim and hope for that is that machine operators don't need to know how to acquire and log that information, even write LabVIEW and get all of this information out. They've got two real areas. They know the information that they want, but because they're researching that particular component, and then they want to sort of pull it into some sort of MATLAB or analyze that data to make comparisons to say this is good, this is bad. If I increase my feed rate or if I use this cutting tool, and that's where the grey box is, because previously what everyone kind of did here is they just did point-to-point solutions. So they would buy a system that did what they wanted it to do, and they would get some data on their local PC, it would live on their local PC, and they would stick it into MATLAB or whatever and try and analyze it. Very sort of academic approach, rather than let's try and think about things and the tasks that you're trying to do to replicate and get that data flowing in a consistent, relatively tied up manufacture. Feel free to chip in. So myself and Richard, my colleague, who's actually left yesterday, so we divided it into two areas. So this diagram is quite simple, but there's quite a lot of thought gone into it, which maybe doesn't quite do it justice. Is we've got instruments. So in a LabVIEW specific environment, we want to focus on that. Our instrument could be a C-series card. It's the physical interface that allows you to do that acquisition. So that could be an analog card, and you plug your power monitoring thing into your analog card. The instrument controller essentially is your computer with any computational power that you want it to have. If it's just a Windows PC, that is what it can be. It can be a compact Rio, it can be with an FPGA, so you've got more actual computational power. I think it was stuff with the NI that they were talking about, where does your edge computing lie, with how far out to the edge does your computational capability go. So you could conceive you actually could have quite intelligent instruments that do very specific things. So you have an application that's dedicated to doing that, and that will be able to connect up to maybe a land network. So focusing on NI, at the moment what we have set up, I've got a old compact Rio on my desk that has all the software to connect to the LAN network and prod and poke that SQL database to allow you to push information up, drag information down about the system. So any kind of forum, any questions in terms of explanations. So the embedded computing side, our mind says everything the other side of the LAN network, because to kind of cross that boundary, your time goes to pot.
Yeah.
And one of the things there which I'd love to get your feedback on is actually this control element here. That when you make an acquisition, if you have enough knowledge about the known performance, you potentially could correct for that error or deviation potentially. So maybe if you could think of it a very simple PID controller or something like that, you have a axis or something on a machine tool that that goes out of tolerance or something, you could conceive that you could try and correct for that. So that's a bit of an aside, really. But yeah, so that's the embedded side of things, and that's what I've been focusing a bit more on. And at the moment, that is in LabVIEW entirely because of its ease, scalability, flexibility. A couple of things, so like the Arduino stuff, is it possible to actually have, rather than a big compact Rio, a couple of £1,000 chassis in there, would you have an Arduino kind of capability in there that you could write some C# C++ code that could communicate with databases and still fit within this kind of framework that we've conceived, really.
Yes, so that's one of the things that we discussed before was to make it, the idea of this is to make it reconfigurable to any target process on the left-hand side. Right?
Yes.
So
software definable.
Absolutely, yeah. So everything's got to be flexible, and I guess personalities have got to be interchangeable. And that's a lot. Well, depending on which type of process you're working towards.
Yes.
And so it's an interesting problem. Well, it's an interesting project and challenge because how do you make everything talk to everything?
Yeah, and that's ultimately, and looking at the instruments here, these arrows here, you've got so many variant sort of communication protocols that you can have. Any one of you could go, oh, well, that's Bluetooth, or that's Profinet, or is that, there's so many industrial layers, but then also there is an instrument that talks that language. So if we can cater for those different instruments, we should be able to implement different target processors and things here. And where that computational power goes. And at the moment, our definition really of this controller is basically anything that can connect to a LAN network, whatever that may be. That has to be a LabVIEW specific thing, but I'll talk within the context of that.
I guess there's one other thing that maybe I'm not sure whether I fully understood this. Trying to explain that. But the idea is also have all that data available to an abstracted user, so they don't see the instrumentation side of it. Right? They're the person who's setting up the process they want to work with through some sort of abstracted interface, right?
Yes, very much so. Which kind of leads us on to hopefully what I should be able to show you. So what we have. Yeah, we've got a few windows there. So what we have here is the web page. essentially. This is quite a development-based page, and there's quite a lot of stuff behind it and a lot more thought, really. So, excuse me if I go into a little bit of detail on this web stuff, and it's not LabVIEW specific, but we can get back into that side of things later. So at the moment, we are in the realms of the IT platform. So what we have is a virtual machine that's hosted on one of our servers over there. So it's just a window, it's just a PC, and that is hosting our website and our SQL server, and it's also hosting the file store and all of that information. So one of the things that you probably can read there is what we tried to do is if you flip, I think, to definitions, so we're talking relatively the same language. So one of the things here, in terms of the scalability and flexibility, is trying to, group understanding points, really. So as I've touched on here, we've got an instrument, a type of physical resource, optionally soft resource, instrument controller, with that capability. Yeah, sorry. So a physical resource, as you can read, is some sort of tangible asset. Within this project, you see a fixture, a big piece of metal, a machine. Soft resource is your way that your CNC file or G code. And the reason we kind of went to the level of thinking about this is because all of these things need to be captured to understand and process, the information, because you need all of that metadata to actually contextualize what you were doing and what that information is. There's no point just having the raw information and then you try to infer meanings, and you lose the context and the quality of that data.
Yeah.
So the point was, if we can take that picture, that snapshot of what we're doing at that particular point in time, you've got a good foundation from what myself and Richard could conceive to say, actually, on this day, the cutting tool broke because whatever. Feel free to stop, interject, wherever appropriate. So now we kind of move on to, let's pick up on the task definition. And as the word suggests, it is what we want to do. So it's the target process, it's the definition. So if we go onto our website here, what we have, I can do that, is, so we've got physical resources. So this is all pulled from our SQL database, which is here, my SQL database, should I say. So we've got a list of physical resources, and if we wanted to, we could add a new row and push that into there. We could also list our soft resources. So if we go to the diagram on the wall where the user zone is, this is where we're looking in here. So if you're someone that wants to, I've got a new piece of whatever, you could go, right, let's push that information into your database. So here, so we've got, and at the moment this is kind of dummy data. This is very early to development concept proving that you can do. It's not bells and whistles or anything. So what we've said, we've come up with the idea of a power sampling definition, and that's what it is. So I shall now go into the world of XML, hopefully, and sort of give a bit of meat on the bones as to how all of this is hanging up and hanging together. So, task definitions. So what we have is task definition files. So, appreciate any thoughts and feedback. And coming back to Mark saying about flexibility and scalability. So with XML was one of the vehicles that we chose to actually take into account, for all of that flexibility and things because of the, the nature of its design, etc., etc. So let me just, I believe this is where Richard's knowledge would be nice and useful, but this is okay. I shall not on here. So I haven't got XML notepad to see me. So up here we can see a method name. So we've conceived that one of the ways is to monitor power is either 3-phase power, or another method is 1-phase power. That was just the thoughts that we had. And you can sort of trigger through here that, how do you want the results? You want them in CSV and you want them in this, and the values, and you sort of read those. And rising edge triggering and different things like that. You've got some revision numbers, what results do you want? We're going to have voltage red, blue and yellow. We're going to be in units of volts and things. So this, if you look on there, we've got a research user. And this is what information they would kind of populate. They're the drivers behind the system, so they know what they want out. So they should be able to develop this XML file to, based on maybe a template of, understanding. So all of this information there is what goes and it pulls on this. So I selected task definition on there. This one. So power sampling. So it goes off to the power sampling definition in the XML that's on our file store. So the page does that. It comes back with ways of doing it. Okay. So you can do it in 1-phase or 3-phase, and then it says, right, okay, how do you want to do it? Essentially, so you've got physical resources, soft resources that you can select. You may want to change some of the parameters, the sample rates here, so you could edit those and things there. So what I should now do, hopefully, is pop down into here, and this is where LabVIEW kind of kicks back in, hopefully. So I've now, and I'll run it through there. So one of the things that happens, just a moment, when you create this task, what it does on the SQL table, you basically have a big to-do list. So you can imagine that you've got these instrument controllers around, and you've got instruments attached to them, and what it is essentially looking, saying, can I undertake that action or that definition to the instrument controllers are continually polling the database to say what new tasks have been created and can I do them. Okay. So based on the physical instruments that are actually connected to them, you're saying, I've got an analog card, you want to monitor temperature, yes, I can undertake that. So it kind of just grabs that data, and then it will grab all of the XML data from the file store and pull it down onto the instrument controllers.
So which one's in charge of that? If the instrument is
the instrument controller is doing the grabbing from the SQL database. So at the moment we're pushing all of this information into the SQL database. It then sort of sits there in a state of new to say,
Right, so you're saying there isn't like an overall controller, each instrument controller is kind of a little bit of distributed brain.
Yes, very much so, and that's kind of the hope that, this is where maybe computational power is at the edge computing, how it does. So at the moment, the LabVIEW kind of thing, the LabVIEW has got the SQL database communications, so you use your queries and stored procedures to push the code. So I shall set this off running, hopefully. So this is deploying onto my desk now. So this is where it will go.
Right now.
I plugged in the LAN network, that's why. So one of the things here, I was trying my best this morning. I shan't use those words, but okay. So I've just got a host VI that I'm using for sort of regimen's sake. So now let's create a task. So we're going to just do it on a sensor tag, and I'll create that task. So we're going to say that's what we want to do. So it creates a task of 1031. So hopefully now, so it's now picked up that task out of the database with 1031 as the ID. So this is now the instrument controller that's picked up that task. I've got a oscilloscope on my desk that's running just a square wave generator. So that's a Sigma Delta FPGA on the compact Rio that's doing that acquisition. So now, if I literally force trigger, I'll do that, which is okay. Stop it and restart it. But in preparation for this, that force triggering is essentially is basically just triggering the system to send information back up to the SQL database. Okay, so if you imagine your target process is now it's been taken and it's gone off and done that target process, whatever that is. The way that I'm just triggering it is just over UDP to sort of say, right, give me what you've got to date. So in preparation for this not running seamlessly, because I knew there was a few bugs, but this is okay. So now we've triggered that process, and what we should is what task did we create? 1031. There we go. So this is a bit of dummy data that I from previously. So when I was doing it earlier, it owned that task, and then carried on doing it. And at a point when I triggered it, I've just set it up to generate a sine wave, and that sine wave is SQL queries back into the database table of all of your data. Okay, so all of that data is then populated in this information here. So it then pulls out 1031 wherever that task ID is.
So is the idea that the instrument is streaming that to the database, or when it's finished its task? If you're not querying it from your UI?
Either, potentially. Yeah. You could sort of say, right,
store it locally,
and then if you look in here in the actual database, there is this one here. So if you don't send back raw data, we can see, well, you can send back a file, which is a TDMS file, and it's a pointer within that file store, and it's, you know, it could be a maybe a vibration or in acoustics. So you've got loads of data, and you can't query and send all of that back. Let's log it and then just literally send the file pointer back. Yeah. And then you will be able to go and download that file and interrogate it and go through it.
What everything else that's in there also comes in that file? Yeah. Are they just like the single readings?
Yes. So what's just 5 questions and then I can do best to answer. So at the moment, this is where Richard spent a bit more of his time, and you know, the web side of things is something that is to develop further, really. But in terms of proof of concept, so in terms of this sine wave, this is the task ID. So we created the definition of what we wanted to do. We owned it, And then for dummy data, what I've done is just created SQL queries using the stored procedure to send this information back. So it's just continuing just polling and pushing that information back. This page here, then, is what you should be able to do, which probably won't set up quite yet, is if you wanted to compare data between different tasks. So if you've got two asynchronous actions, you should then be able to map them against each other with respect to time.
Nice.
Yeah. So in terms of, you know, you've got one task that may be monitoring the ambient temperature of your shop floor, and then you've got another task that was doing some high-speed acquisition. You know, you may want to say, oh, is there any correlation between those with respect to that period of time? And this is the world of web development to make it, you know, user-friendly and things. And you know what we're trying to do here really is just show the concept and not the thought process. So I'm not sure whether this would quite show, but you can imagine that you have this sine wave, and then, you know, 1028 task was a different voltage, and you would have some, you know, maybe different readings that were presented, and you could go through from there. So I don't want to sort of keep shouting or just disseminating information sort of thing. So yes.
So I'm just getting this right. So you're receiving data, and you're every sample you're pushing into the database as another row.
Within this context, yeah.
Because previously, I mean, there's probably many other ways you could do it, but the like you've got there is my value. I've got something there. Yeah. So there's just one row. And you see, you would have, right, okay, task ID 1027. Yeah. It's just one row, and you just pull out the my value was an array. Now you can just it just saves you having a massive table.
Right. So like when you have a file function there, you have a file function to DNS or file function.
I mean, you could do that, or let's say you could set up as an XML form. So it's a string format, but when you pull it back out into your software or view or whatever, you can say, okay, it's an XML format of this.
Right.
Of a 2D string, but the 2D number, let's say, and that's it. That's and it's just saves. You can look at this and go, oh my god, I've got 50,000 points for 1027, whereas I can just say, oh, I can just have 1027. And this is how it does it.
Yeah. Okay. Yeah. That's
it's just
that's one way. At the moment, you know, we've kind of covered that by saying,
file,
you know,
exactly.
with the file, and that would, you know, web development, we can say, right, you know, you can see potentially, you know, on this page here, you've got a file download, you know, and you just grab all of that data and do that. So definitely, that's, you know, that's a.
I guess this is probably a simpler query, just first off. Getting all the rows and just getting the data.
Yeah.
And then
So at the moment,
you
to try and sort of, we're just at the stage of literally merging and tying everything back together. That I, in the lab view, just down here somewhere, whatever VR, with which one? No, the other one. So this is one of the threads, the login thread that you can see here. I open up the IP, the authentication, the credentials, and then I've just kind of just shown that I can then communicate those information points back up. So it's got the sine wave generated and pushing that back up with SQL queries. It's not the neatest kind of way, but it's a way for us at the moment just to prove the concept that what we can do is we can define a task, we can undertake it, we've got the XML flexibility, we own it, you know, in an embedded system, we undertake it and we set that off running, and then you have the ability to trigger and push information back up that tree. So yeah, there you go. that's where we are to date. If people are interested in the details and the technical stuff, we'll go through like some of the admin code and bits and pieces. But one of the main VIs is we run out of hurdle.
What are some of the challenges you're facing?
So one of the biggest things at the moment is this is for one target process, for example. So we've just defined a power monitoring task that we've got our little C-series card in, and we can do that. So one of the things I'm working on at the moment is what's important to some of the technicians is, okay, we've got this power signal, but what was happening when that power signal was occurring? So you have on CNC machines, you have your G code, which is what it was doing. You know, is it doing a straight cut, a fast cut, machinist, all these different things.
Yeah.
And you therefore then actually have a third-party target process. So we've got a CNC machine that is £100,000, and it's quite capable of running itself, but I want some information out of that machine. So one of the things that I do have, I'll get it when I'm not, I'll share it later, is that you have a connection into that machine via TCP/IP and Ethernet, so you actually plug that machine into the room, and you have the libraries of that, the functions on that machine that it can do, like monitor the x-axis, or open a connection, close a connection. So you can do that on a Windows PC, and you can kind of prod and poke that machine to get the information out. However, within the sort of architecture behind it, hope was, well, if we can push this down onto a compact relay, I can prod and poke the machine, if this is a machine, I can do it over a local kind of connection. So now you've got the power trace, you've got the state of the machine at any given time. So you have two pieces of information quite tightly coupled.
Yeah.
And potentially then, does that open up the option of the control, for better real-time control, that you're all the other side of the LAN network. Don't get me wrong, you've still got time-related issues because, how long does it
It depends on your processor, doesn't it? If it's a temperature thing, then it probably doesn't matter.
If it's a
speed control. Yeah.
You're then dependent on, how long does it take to throw a TCP query, get the information back. But some applications you could live with that, others you couldn't. Not sure, that's future investigation, so we work.
So does the code running on the instrument controller to control or to read the instruments?
Yeah.
Have you kind of defined a specific API, if you like, for that? Now I know it's kind of doing, in this case, doing NI stuff, but
yeah,
it'd be interesting to see whether there's a definable interface between the program that's logging stuff and the instrumentation, because I guess where I'm going is that you're kind of talking about your CNC machine being just another instrument.
Yeah.
So if that API is the same as you would be talking to your NI key, I know it's not.
Yeah.
It might be just a bit more.
A lot of the stuff, and I think that's potentially where a lot of the future development kind of stuff. Going back to you saying now it's apps and APIs. So what, in my mind, is you'd almost build up this software library of going, well, okay, now I need a Bluetooth instrument. Okay, I've got my API for that Bluetooth because it's either written in LabVIEW or it's written by another.
Yeah.
We've got the way of communicating back up to the network. So if we try and standardize, and this is where, with the software side of things, I don't think you can ever standardize it. But if we can say we've got those API modules that you can deploy onto either your FPGA if it's a Sigma Delta, or if it's onto a compact Rio. You know, we've got some of that things, and this is where you know, that software-defined API, you know, love feedback and thoughts really, because we've kind of got it to this stage where it's like, okay, what, you know, open it up to the forum to say, you know, is it of value, is it of use? I think we see quite a lot of value in it within here, and hopefully, you know, in all of the Internet of Things, all of this connectivity kind of stuff, is that you know, there's thoughts and things for yourselves, and feel free to feedback on it. So it was our thought really over the last 6 to 8 months. You know, when PTG came to us with this problem that they had, that, you know, they just keep buying end-to-end sort of solutions, and, you know, they never just have one way of doing it, but just kind of plug in some adapters to kind of make it flexible. They just go and buy some new stuff. And if we can move it to maybe more software target tool, you know, you've got
Because essentially what you're doing is data logging. I mean, not to be.
No,
It's simple data logger.
Yeah, this job we're doing out in China is just a simple data logger.
well, that's what, you know, for a lot of things, that's what, you know.
But what,
Sorry, go on.
no, I was going to say, but what I'm saying is that even a simple data logger can get quite complex when you're talking about lots of different protocols.
Yeah.
But the way I'd be inclined to approach it, which I think you're doing anyway, but is to kind of, I mean, these words are banded around quite a lot. This abstraction, hardware abstraction layer.
Yeah.
But it does prove really useful. So I think you're kind of doing that anyway. But I'm just thinking about where because you've kind of got the standard API between the SQL and but maybe this between here and here, I think that is a bit more standard. Just allows you to have that type of control. So you imagine your acquisition could be coming through Connect or whatever, but then your control might be, you know, over Modbus to your. So if you have literally the data sources to the instrument and the controller being able to just effectively map, if you like, those inputs to outputs, or through a PID or through a.
I think that's just what thoughts on.
You sort of think that almost instrument control level, effectively like a data dictionary. So you know, it might be that you say that this whole stream of data from the CNC, but actually you don't. That's not what you log. What you have in instrument control, you basically have it saying that if somebody's asking you for the x-axis position, I happen to know that the way I talk to this instrument is by this, so I understand the concept you have for the super x-axis. I say that I have like my own data dictionary, so I actually go like, I'm going to take this from this particular instrument, so that map it and return it to you, and realize labeled as x-axis position. So actually you end up putting like a layer of data abstraction.
Very nice. So
if you guys know me, I'm going to sound like a bore, but it sounds like the whole Veristand thing came out of this kind of idea of kind of mapping and making something configurable for people. That you have kind of custom adapters that allow, you know, in Veristand you have a custom device that allows you to do Modbus, but basically all it's doing is putting data into the system. It's a channel. Everything in Veristand is a channel. And then you map them together, and then you can map an input to an output, or you put it through a model, and a model is a PID, for example. So that's kind of, but I'm not saying that you should use Veristand. I'm saying about the concept of creating all the channels in.
That is, I think, it's something like the concept, isn't it? You're taking that same map and you make it, you know, it really can do a
scale it, all that.
Do a first level analysis.
Yeah.
Because actually what we do, we take some good analysis and to resolve that analysis is sparse packaging or into your, because effectively your SQL database, so you don't want it to be a complete set of all the data you have.
No, definitely not.
It just needs to be the warehouse for what you can find and make sense of.
Yes, and that's
far more data. There's far more transactional data.
Yeah, you want to filter and get out all of that.
Your controller. So you want to just get that transactional stuff at the edge.
Yes, project feedback stuff that actually makes sense from your models.
Exactly, and what you deem as useful there. Yeah,
I like this idea of being able to define your tasks and do that down.
That's-
Saying you do have these instruments that sit there and go, I understand what that is, and you know how to deal with that. And then instruments that don't have that, you say, look at developing on that instrument, control that.
That's really nice. Yeah, I really like the way you've gone about it, especially with that.
I was really just going to say that that's the software API side of things is, you know, it's a huge possibility to, you know, right, okay, I've now got this, okay, right, I have an API for that one, and if it can talk and say like you're talking about those channels and those nodes, and you're providing those mapping blocks, as you were, because this is more on sort of the hardware conceptual side of things, but you know, there's the same kind of philosophy for software for writing that. It's just the fact that when you got around to it, and there's probably only me. It's understanding it, you know.
Yeah.
So, yeah, I don't know quite if I haven't been doing a bit like the only other one, I'll just put all this kind of bed things. If you're all going through a bit more detail and stuff, I'm happy to try and answer some questions. The only other thing that I was going to kind of probe and then ask for some advice is this. So the other diagram that I printed off is for we have an EPSRC project that is to do a laser 3D laser printing machine. And it looks a bit like this.
Additive manufacturing is essentially the process of joining materials to make objects from 3D model data, so computer-aided design or CAD data. This is usually done layer upon layer. What high-speed sintering does is replace this laser system with an infrared lamp and an inkjet printhead. We have a bed of powdered material, and then what we do is input thermal energy into that bed in the form of an infrared lamp. The inkjet printhead prints an ink containing carbon black, which is an infrared radiation absorbing material. So we print ink in a desired cross-section, and then the infrared lamp will pass over the build bed, and the cross-section with the ink will receive more thermal energy than the rest of the build bed due to the carbon black, enough to sinter the powder. And then what we would do is repeat the process, so deposit a fresh layer of powder and repeat the process until we have a completed 3D object. What we've done in this research is change the amount of ink in the cross-section. What we've done is have various densities of black dots with spaces in between, which changes the amount of carbon black within the cross-section. What we found was that at the parameters commonly used for manufacturing nylon 12, we're actually using an excess of ink by printing in fully black. We observe much higher tensile properties, so ultimate tensile strength, elongation at breaking Young's modulus, by printing at lower ink levels. So this research will allow us to produce parts with much higher mechanical properties than we've seen before, allowing it to compute with processes such as injection moulding, whilst at the same time reducing our ink consumption, which saves on relatively expensive ink costs.
So there are a number of applications for this technology. One obvious one is to make use of the fact that we can start making parts that have different properties throughout different parts of the part. So for example, we could make things like outsoles for running shoes, which are quite stiff in certain areas and relatively flexible in other areas, and we can do that all with one material. So another potential area to take advantage of this technology is the fact that we can make parts that have different densities. So for example, we can make parts that are quite stiff and dense on the outside, but low weight in the middle. So we can start lightweighting parts for transport applications in automotive and in aerospace, for example. From a sustainability perspective, this is also very exciting because it allows us to make parts with a variety of different properties, but all using a single material. So this means at the end of life, recycling or reusing of the material is far easier than if we'd had to use lots of different materials in a single part.
So this machine lives at the university's Adams Centre in the main campus, and it's quite a small building area, little parts. So this project that was being awarded by EPSRC is to produce a machine that is capable of printing very large scales, which is where they get the idea of printing
comparable to
Injection
moulding. So the build area the machine that we've got to produce is 1.6 metres by 1 metre by 600. So maybe about 2/3 the size of this. And they fill that with a vat of polymer, these polymer beads, and we have the same process of printing and everything like that. So that's the goal of the project. We've got 18 months to get a system working. So one of the things is that we're working with some of the guys at the admin centre who are a chemist and mechanical engineer. We've got 5 other mechanical engineers developing the thing. So we have 1 software engineer, which is me, and systems work, plugins here to do a lot of the development. And yeah, so I kind of want to use you a little bit of a sounding board and a knowledge board we've got on this, because my colleague Richard moved on yesterday. Didn't really have that as much. So this is where this sort of user group forum. I sat down the other week, and to date that's a diagram that I put together of all the things that I think are in the system. So we'll get up and have a closer look.
You read some of them out, just the Bible.
Yeah.
Do you know them off by
I do know them. I spent some time looking at them. So if we go from just left to right, you've got a block that I can see is power management and monitoring. So that's everything within the system, that makes it safe, everything related to power, which I thought was a good starting point. This system's going to use quite a lot of power. And to understand that is, I've got another kind of yellow block, which is what I think is a compact Rio-based system. And looking down it, I've put in some scope for maybe some vision system to look at part recognition and understanding, locating as to how the print, that inkjet printer goes across. You've then got in those top 4 boxes the feed screws. So you've got powder that's coming up from stores up to the bed, and then you bring the roller across to actually distribute that. On the video you saw it going left to right. So our system has got to print bi-directionally. So you have 2 screws at either end, and that's what those are that bring powder up from the lower hopper or up to the base there. So within the system, you've got 10 feed screws that is bringing this powder up. One of the other things I kind of forgot to mention is that the process is that you have this powder mass, and it's kind of at a state that's sticky. Okay, so the crystalline curve of the chemical properties are that you heat these polymers up and they get excited and they become sticky, and then the energy from the lamp passing over basically takes it over their melting point to give it a kick of energy. So you now have 2 layers that have been bound together, so they're sticky. And then what you have to do is keep the whole thing at that sort of 150, 180 degrees state, and so that when it cools, they don't shrink and morph shape. So as that suggests, what we need to do is kind of heat this powder up to the surface, and we've got some heating jackets to maybe do that. How that design works, I'm quite sure. Anyway, and then as temperature is quite important within this system as to how it's going to manage it. how you're going to keep that temperature consistent.
Is that quite a localized temperature? Or is it the whole bed?
It needs to be very even across the whole bed, so that as you're printing, that you don't get differential pockets and all of these sort of things. So we have, you can see somewhere, quite a few pyrometers that are testing the bed for temperature. So we've got some of that there. You've got some control of the sintering lamps, so the lamps that are coming across. We want to control the intensity of those to give the research user, ability to optimize the processing system.
So is that here raster scanned, like going across as it moves?
So
or is it a bench of lamps?
It's on a whole carriage. So there's a big carriage that basically.
But it's got lamps all the way across it.
And it'll have one lamp across the width. So it'll be one IR lamp. IR lamp across the width. So we are wanting to sort of set and control the temperature which gives you that kick of energy. Single one. Well, I'm sure. At the moment, it's 1 meter long lamp that has a response time. I think it's got that full temperature. 15 minutes, supposedly. Not sure if I'm trying. From turning it on and it getting up to whatever you turn it on to. And then I think the next box is printing technology, which is actually being supplied by a third-party company which does all of the inkjet printing of this carbon black. So we've got some interfacing with that to deal with. The next bit is all of the heating. How do you heat all of this volume of powder and manage it? So I've got some heated jackets and thermocouples in there. Then you've got all the motion and control of the Z stages. So in order to drop the bed down, it's got to have a tolerance of about 0.1, so about 109. And this build volume is about it. And then you've got the X and the Z coming across, etc., etc. And all of those heaters and things, at the moment, I think are going to be controlled by some thyristor switching to switch them on and off and something else. So it kind of then comes back to, I see LabVIEW as one of the vehicle to do this, and thoughts and opinions on how to go about the software side of things. But so just to build a really thinking. It's going to be a bit cheaper. No, so the point of the actual project is there's no other machine in the world that exists doing this printing technology in this way, and the value is to get it to print on large scale. Some of the guys out there that bought similar 3D printers and they're 200 quid. This machine is going to be far from that because the cost of buying the polymer is about £5 grand. Is getting into the technicalities and the point of it all is, the more you think about it, it just becomes viable.
What's going to be the limit? Do you know what the limiting factor in terms of, because all of these things kind of speed is probably, you want to push the speed. Yeah. But is that going to be like the thermal issues is probably?
One of the, I think the limiting factors is the X stages, because this machine is massive. And how quickly you can pass across, roll, print, sinter, the actual, that is how, the determining factor, how quickly you can go from left to right and back again. And if the whole volume were printed, I think we worked out, was it just 72 hours of continuous printing? So this is where, is it quick?
Is it? Yeah. I'm guessing it's just a rolling print. It doesn't get to the point, stop print, get to the point. So it's just a,
Well,
you would roll from one side to the other.
yeah, but and then roll back, and then it will sequentially. It should be quite a straightforward kind of operation. Going well, you start here, you print this way, and then you stop, and then you print that way, and you drop down each time, and you reload the new images in, and so. I feel like I've probably taken up the talking time, so I should kind of stop there and hand over. If you want.
What sort of challenges do you guys face when you try to approach a project like this? What's some of the tips?
Subcontract a lot there.
Yeah.
So, I mean, it sounds like, I mean, there's going to be a lot of subcontracted bits here anyway, isn't it? I mean, so maybe all the printing stuff is subcontracted. And the stages, are you thinking about controlling that all like NI stuff? Or?
At the moment, the stages have been spec'd as some Parker Hannifin stages and single axis drives with a Profinet connection. However, I think one of the biggest kind of challenges I can see is the sequencing and the orchestrating of all these bits of instrument, because in their entity, you know, turning on, doing some thyristor switching in the PID controller of the RAM, it's not really very.
I guess that's my question came on the speed of things, because that's really going to dictate, isn't it?
Is there how much do you want? Double check. So if you want the vision to double check that the carbon black position is correct before you center.
So coming back to the point that I made earlier about one software engineer and 5 mechanical engineers, if there was a slightly more biased the other way, to think the system and the software and the user interface and experience of what the system can do would be different. Understanding that there is a limited software resource kind of tends me away from that. But this is why, you know, the modularity of, you know, the MI stuff, you know, okay, it's not cheap off the shelf to make this a commercial viable system. Probably never is going to be. But if you're giving the flexibility, you know.
So you can build it in there without vision double check. And if there's kind of problems, you then introduce like that, especially with like a real-based system.
Yeah.
What would be interesting as well, because I know you've got 2 cameras in there in your vision. I think it's I think we're going to be putting an NIR, a near infrared camera post scintillation light. You can just actually see if you can tell from the residual heat pattern. Right. So as you've gone over the scintillator, can you actually detect like the residual heat pattern, how efficient that previous transfer has been? Because then you could certainly look at it as a research tool. You can sort of start to play around with the idea that as you change your black deposit, you can see the change in the residual.
I think the 2 other cameras that we've got there are the thermal cameras that we were looking to focus onto the bed. If I understand you.
Well, no, I mean, that would look like, well, I don't know if you necessarily need to go all the way to thermal, but for images, because I mean, you use resolution, but you can even get you can buy NIR systems for Raspberry Pis. So just be able to look at NIR. If you would have to go all the way up to 10 kilometers.
Yeah, at the moment, we're probably going on the thermal side, but
and also depending on budget, what we're so doing happening, you can use the flag cut to new mobile sensors.
Unfortunately, they won't work with their CPU and stuff. So the FPG, they'd have to go into bit of science. Have you ever seen the photograph sensors before?
no.
So the idea behind photograph sensors, optical sensors, and there are advantages for a couple of reasons. First reason is that we're using a fibre optic cable that strips over thousands of meters. And you can also use one for moving state. Yeah, absolutely. Yeah, and the nice thing is you can have one channel with 80 sensors. Some number around. I think it's 20 actually. So yeah, one fibre front sensor.
Usually those ones.
The beauty of them is they do strain and temperature together, so you actually relate those two values together. So the strain gauges are actually self-calibrating the temperature. But it's like there's interest for it, so we always feedback that.
So one of the questions really is, I kind of drew this diagram to really understand things, because coming back to saying about the system understanding, it's obviously it is completely vital that we understand that how all these things are going to communicate, and break them down into the individual components.
Well, what I was going to say, when we kind of take on a big problem like this, that's exactly what we do, and that's actually why we like LabVIEW, because we break it down into the black boxes, and we don't necessarily use the actor framework, but we use the kind of asynchronous modules that are doing their own job. So here we'd kind of take a system and, okay, it's thermal. If you look at these, if you draw this and then dig a bit further into the interfaces between these boxes, the interfaces should be there shouldn't be hundreds of arrows between them, obviously. And if there is, then you've grouped it wrongly. So, and then we tend to write software modules that will look after like a thermal management module, and maybe it has more modules inside it. And you can really then fully, put test harness on that piece and test out that piece of software separately.
This is when you say test as well. There's a point of education and understanding that in our world, that test of that single little software module is where you write it, you've got a wrapper and test bed, and you kind of hand it over to the colleague to say, right, can you break it? What conditions does this not operate as you expect? So that's one thing that at the moment is not a software writing stage, but in the future, we don't have that capability in-house. We have to go outside to actually get some third-party verification. Because this system, even if you said it's running 72 hours, it's could have a big cost of failure. If it's a software bug that only happens once every 48 hours.
Yeah, absolutely.
And I don't think that side of things within the project team is fully considered because of their knowledge base. They're very much more mechanical biased, and actually, a wrongly categorized error could just trickle through and drop everything. Your X stage just holds there with your sintering lamp on, and you start burning metal and you create a fire.
Yeah, absolutely. Yeah.
So,
I mean, looking at a lot of the high-speed stuff on here is kind of dealt with already, like the printing itself.
Yes,
kind
the
of,
actual printing side of things, which is
good.
Dealt with. Yeah. A lot of it is the sequencing and the operation of how you want each of the elements to behave.
But it's such particularly high speed, you almost preload.
Oh, I mean, that's why I said about
you preload the frame and the printing just deposits it. So
there's nothing.
Yeah.
There is nothing really.
The printing itself is dealt with separately. So yeah.
They're talking. Well, we have a common phrase. Mechanical engineers kind of talking like seconds. We're talking like microseconds or nanoseconds. That's what, going back to the framework, well, if we can get it within a couple of seconds, it's like, so, that's where, that's one big differential, when you're talking to system engineering, it's like, 5 milliseconds.
Yeah.
So you've already brought it down to what it seems to be, so you've already got a building block there, what you can start.
It's going to another stage. this was just to help me understand and also to convey a message of what the system could look like.
Yeah.
Yeah.
So
Let's have a digest, and we can always come back to you and
Yeah,
some thoughts.
Just remember, if you're going to pass it about, make sure you have the easy stuff to do that.
or the interesting bits.
Yeah.
That's you at the top then, is it?
That's just
Yeah,
as well.
it's true.
Hiding behind it.
Hiding behind it. Should have really joined Richard. I should have put a door. But yeah, thank you very much for listening.
No, thank you. That's a good insight. Thank you.